Yeah, I kind of mentioned in the email this. I don't plan on going too crazy uh, with the workshop today. We very well may finish early. That's ambitious. I don't know if I've ever finished a workshop early because I tend to talk too much, but you know, uh, there's not way too much to talk about this week, especially because uh, I guess I watched I skimmed through the lecture that he gave, and he covered. It seemed like he went through all of chapter 23 or whichever one we're on, the one about sugars, but he's going to talk more about it. So uh, it didn't end with the Thursday lecture, so we don't have to like go through everything, and we'll have next week too to work on it. So uh, I kind of just want to talk about like the big ideas here, and then we'll start going through some of the problems that we have for this week. Um, Yeah, we could talk about those. And if you have questions along the way, please ask. Um, we will probably have the time to talk about whatever questions you guys have. So that is important. Okay, how about I start writing? Um, so this is for chapter 23, which is sugars. Uh, and to be more like I guess specific, this is an organic chemistry class, so it's for saccharide chemistry. Okay. Um, and the important idea for this chapter is particularly that here we're using the Fisher projection, and we haven't done that very much before. Uh, Maybe some people from Daily talked about it or covered it, or if you took Organic Chem 1 in a different semester, you might have seen it a bit more. I know for like Professor Molander, who I worked with last semester and who I took Organic Chemistry 1 with, uh, we didn't talk about it very much. So the whole like idea behind the Fisher projection is that you draw your stereocenters as this cross and you write your substituents, around the cross. And what this corresponds to is the things on the top and bottom go away from you, and then the things on the sides go towards you. Okay? Uh, Maybe one way you can think about to remember this is that you have a bow tie. So the bow tie, like, goes to the sides. Um, I don't know if that's a helpful way of remembering this. I just pulled it out of nowhere on the spot. So uh, this is one thing that like is good to be familiar with, and it is useful to know that this is like the way that the structure looks uh, for when you start working with much larger things like sugars. Okay, so what I have drawn here is our first sugar, which is D-glyceraldehyde. Okay, that's the one that I've just drawn here, and it's either of these two projections or drawings is D-glyceraldehyde. These are the same structure. Okay, so in terms of the general structure, sugars, when you draw them, so at the bottom, they will have CH2OH. That one is like always going to be there as far as I can think of. And the sugar, the alcohol right above it, if it's on the right, let's see, maybe I'll use a different color. So if the first alcohol is on the right, then this is a D sugar. Okay. If it's on the left, then this is an L sugar. Okay? And from there, there's a whole bunch of stuff in the chain above. But what really matters is at the top, either we have CHO, so this is an aldose or aldehyde, or we can have an O, like a C double bond O in the middle, and then this would be a ketose. Okay? So this alcohol is always at the bottom. Oops. And then either we have an aldehyde or a ketone. So we have an aldose or a ketose. Um, and I should say a ketose at the top will have also a CH2OH. Okay? So we have these features of our sugars. And that pretty much covers the what defines a sugar. Each one of these carbons, so each one of these like stereocenters will have an OH or an O like methyl or O ethyl or whatever, right? And also a hydrogen. Okay. So, all right, let's draw an actual example. Okay. And I will pick this is the most relevant example that there is. Okay. Here we go. Okay. So this is a D sugar, and specifically this is D-glucose. Okay. This is one of the sugars that I know for a fact that you should know the structure of. Um, for the chapter on sugars, I I can't remember exactly what things you have to remember. Like I know for the next chapter, which is about amino acids and proteins, um, you need to know the three-letter codes of the amino acids, and you need to know the steps of synthesis, the like solid phase synthesis or whatever. For sugars, I can't remember exactly what he said to what names he said to remember. I know that you need to know glucose. You should probably know fructose. And well, I can't remember what else. Uh, if anybody did hear in the lecture what things he said you should remember, maybe chime in. But well, I can't remember.
There was a couple he told us to remember. It's on the slide, but it's like a good handful. I don't know if you want me to say them out loud now.
Oh, okay. So there's more. It might be all of the six carbon sugars, maybe.
It's glyceraldehyde, erythrose, threurose, ribose, arabinose, xylose, and lixose. There's a lot of
Wow.
sugars in the aldose family.
Okay, so that it sounds like it's all of the 3, 4, and 5 carbon aldoses.
Yeah.
Um, okay. Yeah. So, well, follow what he said in lecture to remember. Um, I think historically, when they give you a compound, when they name something on an exam, they usually tell you, but if he tells you that you should know it, then I guess it's still fair game, and you shouldn't take the past as precedent. but I think in the past they've usually given the structures of things. Um, you should follow what he says for remembering them, but usually it hasn't been like the remembering the names of the sugars hasn't been the biggest thing that there was. Yeah, okay. Yeah, so we have here, this is glucose. This is just probably also a good one to remember, like in general, I guess, like for anyone who's interested in like biochemistry stuff, or like probably just if you want to be a doctor, you probably just have to know this. And I know that that's relevant for a lot of people who are taking the class. So, uh, yeah, this is a good one to know. And then what we want to do is to draw this as what you've actually seen before, which is, let's see, this guy, H. Yeah, so this is what we want. And we, currently definitely don't have that. So what we need to remember is that each of these bonds, or each of these, you know, uh, crosses here are stereocenters. So these are all sticking out. Okay. And what we want to eventually get is for, we want this OH at the end. No, sorry, wait. We want this OH here to go up and attack at this aldehyde. Okay. Um, but we can't really do that as in the position that it's in right now. So what we will do first is we will take this structure and rotate it 180 degrees like that. Okay. So we're not taking the mirror image, but we're rotating it. I can't draw a straight line for my life. There we go. Okay. And then CHO down here. And then we're going to flip these. Okay. And this step is a little weird. I'll show you why I'm doing this in a second. So this OH will come onto this side over here, here, and then fill in the rest. Okay. So we've rotated it. And now since each of these are, sticking out, what we can do is sort of take this structure that we've drawn and we want to kind of fold it over like this, right? So this H will be sticking towards us, and then that OH will be facing backwards, right? And likewise here, this H will be towards us, the OH is backwards, okay? And we keep filling in. Go. And oh, whoops, I drew two OHs here. So this should be just an H. Okay. And so now this OH is facing away. There we go. Okay. And here we have a CH2OH at the end, right? And we wanted to attack with this OH here. So we need to rotate these guys around, these three at the end. So we're going to move this OH over here, this one over here, and this H back there, right? So to draw this again, now we have an OH at the end, and we loop around to have this H over the aldehyde at the end, right? And now we fill in the rest of our structure. Okay. So this CH2OH moved to up here at this position. This hydrogen moved to the back position, and the OH moved to be in plane. Okay. And now from there, here we go. Throw that there. And we can actually take this bond and just give it to a hydrogen. Okay, so we've made an alcohol here now. And there we go. Okay, we've now made a ring, we've closed it. And now I can, instead of drawing, bent lines, I can actually draw straight lines. So this CH2OH is going up. This H is going down. Over here we have an H up, an OH down. Okay, next one over, the OH is up, the H is down, OH down, H up. Okay, and I didn't say anything about this aldehyde here at the end. I didn't say whether it's going up or down. All right, and so the thing is, this attack can be coming from above or below. All right, so what happens is that we can either have the OH going like this and the H like this, or we can have the other way around, which is the OH like this and the H like this. Okay. So what I've drawn here in black is the alpha form, and then what I've drawn here in blue is the beta form. Okay. And alpha and beta are called anomers. Right. So what you usually draw is just, here's your sugar, and you just draw something that looks like this. You use a squiggly line if you want to denote that, like, it could be either. It's either alpha or beta for your sugar. Okay. Yeah, so that covers the whole structure aspect of sugars, right? So whenever you have a sugar, uh, you can do this sort of process to it. The reason I flipped it 180 degrees here in the first step is so that way we got this O to be in this upper right position, and that's called like the Haworth projection. Uh, this is like the very standard way of drawing sugars. So if we didn't do this flipping step first, then we would have gotten the O to be in, I think, the bottom right or bottom left or something like that. So we would have still gotten the right structure. It just wouldn't be in like the standard way of drawing it. And of course, you want to draw it the way that everybody else does. So yeah, this is what we get as our final product. Okay. Yeah. And then I've mentioned this before, or like, in like the last few weeks, but unfortunately, you've gone through most of the reactions that you're learning in this class. Okay. That's what, chapters 16 through 19 were. Those were really all of the reactions. And then chapter 22 came back for, have it say. And now from here, there's not that many remaining. Okay. So we can have, there's only a few in this chapter that you really need to worry about. So let's say you have an aldehyde and you want to go to an alcohol. Well, I mean, a whole bunch of ways to do this, right? I drew them in a different way than I normally would, but this is just a standard reduction. Okay. In this case, you would probably use hydrogen and nickel, or you can use sodium borohydride. Either one of those will work. So this will reduce your sugar, specifically if you have an aldehyde. Okay, and then this is your reduction, and then you can also oxidize. So let's say you have an aldehyde and you want to turn it into an acid, then you could just use bromine in water. Okay. Uh, if you'll think back, like very, very long ago, bromine is an oxidizing agent. Even though like you don't normally think of it as one, bromine does oxidize things. Um, Especially like when it adds across double bonds, for example. That's like an oxidation using bromine. It's just in a weird form. But here you can use bromine to oxidize something into an acid like straight away. Okay. And this is like not too harsh of a reaction. So you can also take an aldehyde and a primary alcohol or like a primary alcohol like that, and then you give it nitric acid, and nitric acid is a lot stronger of a reducing agent. So you get an acid plus an acid. So both of these will turn into acids. Okay. The alcohols that are along the chain won't turn into acids. So it's only at the end, right? And let's see. You can also take an aldehyde or a ketone and do this Tollens test, and it will turn either one of those two into an acid. So this is kind of your way of like identifying if you have an aldehyde or a ketone in your sugar, right? And then let's see. And there's one more reaction, which is the rough degradation. Okay. Along the lines of its name, it's, you know, a little bit rough on your sugars. So you take an aldehyde and then you do bromine water and you get an acid, which, that's just what we saw above. That was over here. And from there, you treat it with, let's see, hydrogen peroxide and iron sulfate, which will give you an aldehyde back, plus it pops off a CO2. Okay. So really what this does is this reaction will shorten your chain by one carbon, which that's pretty useful, right? You can then degrade away your chain until you're left with like 3 carbons, and you could, see the properties as you go along. So this is kind of a useful way of like analyzing your sugars. Right? Let me save what I have. And I'll make a new document. Does anybody have any general questions as we go on? Okay, I'm gonna copy and paste the first problem on. Whoops, it's not open.
Did you
I have it.
anywhere?
Yeah, I uploaded the problems. Oh, I didn't put them on Canvas. Sorry. I will be certain to put them on Canvas when we're done. Yeah. A bunch of people were like, last week I like, it took me a little while to put stuff on the canvas, and a bunch of people made me very aware of that fact, which is helpful. So Uh, if any of you bugged me about it, thank you. That's useful. Okay, let me open this back up. Okay, that way I have the chat open. All right, cool. So here's the first problem, which is to draw the structure of this, like, ungodly name. Okay? Uh, so I looked at this problem at first and I was like, okay, this is absolutely awful. Like, I don't want to do this problem. And then I realized, um, it turns out that this is not so bad. Okay? So it just involves, like, breaking down the naming, and then once you see past the seemingly ugliness of it, it's all right. Okay? So here we have glucopyranosyl. So pyranose is just a six-membered ring. So this is just what we were drawing before. Okay. So glucopyranose is just, we're just drawing a glucose. Okay. We're just drawing a glucose. It's in its ring form, which is the more, the relevant form of glucose. Okay. And we want D-glucose for both of them, which is just what we drew. Okay. And one of them is alpha, and then the other one is beta. So that's kind of significant, right? And they're linked at the third carbon of this beta glucose.
How do you know it's linked at the beta glucose?
So, this like parentheses labeling means that the alpha glucose is the substituent. So you can think of it as like 3O, substituent beta glucose.
Got it.
Okay. So in that sense, we would just go here. We can we can just draw our beta glucose. Does anybody want to remind me if beta glucose is pointing up or down at this anomeric carbon?
It points up.
There we go. Yeah, it points up. Okay. And then we can fill in the rest. Oh, how did I fill it in wrong? Yeah, I did. Yeah. Yeah, I filled them in backwards. So the way that I usually remember is that this one is always going to stick up. The CH2OH. Okay. And then from there, you just go in opposites. Okay. So this OH next to it is going to be down because the OH over here is up. Okay. And from there, the next one is going up, then down, and then you have the anomeric carbon, where you need to remember whether alpha is up or beta is up. So in this case, so beta is up. Okay. So
Would you normally draw it like that, or could you also draw the chair conformation?
oh, yeah, you could draw the chair conformation. Um, Typically they're drawn this way. If we wanted to draw the chair conformation, well, we totally can. So maybe just to see what that would look like, it would be something like this. Yeah. Um, Usually their sugars are just going to be drawn in this projection, just because the chair conformation will usually get like a bit messier if you have all of these things going on. But either one is, perfectly fine in the same thing. Uh, this like Haworth projection where it's drawn flat is like if you remember from organic chemistry 1, there's this thing about how like no matter how like uh as long as you're not changing any of the bonds or like the orientations of the bonds, you're just changing how you draw it, then like it's the same thing, right? So it's from here to here, we're just flattening this thing out. So it's up to you. Either one is like perfectly okay. The flattened one might just be like easier to manage all of the things that are being drawn, but you might also find like you're more comfortable with the chair configuration. So, you know, it's pretty much it's up to you, I guess. Okay. And then we want the third oxygen. Okay. So we want number 3. And the way that this uh the ordering works here is that you start with the anomeric carbon and then you go 2 and 3. Okay. Um, yeah, so you could think about it as starting here with the anomeric side, or I guess like you could think about it as like this one being number 6, but yeah, you start with the anomeric side. That's where number 1 starts. Okay, so number 3, and in that case, instead of drawing an H here, we have an O-linked substituent. So maybe let me redraw just a little bit so that things are not as lumped together. Okay, and this was number 3. So maybe I'll draw a bond coming out like this, which is, a little bit, a little ugly, but that's okay, right? And this is alpha glucose, okay? And in this case, when it's written like this, that means it's when it's like glucopyranosyl, that means that it's on the anomeric carbon. So here we go, right? This is okay. So this one has its own anomeric carbon. So it is bonded there. Right? And because this O is facing down on it, then that means that this is alpha. Right? And from there, we start up here. We know that this one is always facing up. And okay, we just alternate and fill in the rest. And there we go. Okay. That is the product. Okay. And you could see that if we wanted to draw it with the change, like the chair structure, then we would have this. I'm still going to draw this, curvy line because it'll be really messy to draw everything uh, on top of each other. Um, and then from there, we have you know, it'll be the alpha. It'll be an alpha substituent. So if we draw the ring looking the same way as we did the other one, then it'll look like that.
Adam, in the chair confirmation for this one, I thought that, I could be wrong, but that the OHs are always equatorial, or is that not always the case?
Yeah, so in this case they are equatorial. Maybe I just drew them
Even
like
at the third at the third one, I looked at the third carbon, like the H was equatorial, but is that not what you meant?
oh oops, yeah. Okay, yeah, I totally
I was like, maybe there's an exception to the rule that I don't know about, but
no. Yeah, they are all equatorial. I forgot about that. Yeah. Yeah, Professor Smith I think always loved to say that like in glucose all of the things are equatorial, which is true. I guess like I could also redraw this one up here to be down like that. Yeah, there we go. Yeah, I could have drawn this structure better. Okay. Yeah, something like that. And these are also all equatorial. I drew these like way worse. These look way more axial, but these are all yeah, they're all equatorial. Yeah. That's particularly for glucose too. Other sugars will be different than that. Yeah. So either one of these, whichever you prefer, whichever you think are more comfortable drawing, um, is totally fine. It's up to you. Okay. Any remaining questions for one? I will pull up two. Here we go. Uh, yeah, let's press that one. I don't know which option I'm supposed to take. Okay. Uh, let's shrink this, move it around. There we go. Oops, I'm on green. Okay. Yeah. So let's see. Optically active D-aldopentose. Right, this is the important part. So aldopentose. Okay. So that means it's 5 carbons and it's an aldose. Okay. So up at the top it's a CHO and down here we have a CH2OH. Regardless of what we had, it would have been a CH2OH down here, right? And up here it's an aldehyde. Okay. Um, just as a note, so I wouldn't worry about like the whole naming process of these too much. I'll try to like wherever it uses the words, like this whole worksheet is mostly just in terms of words. So wherever it uses words, uh, I'll try to show what they're talking about because that's like, that's just more relevant for us. Okay. So it's like this, and then it's D. So because it's D, we know that over here is an OH on the right. All right, cool. So let's see. Upon treatment with HNO3, it gives an optically inactive aldaric acid. Okay, whatever. Whatever that means. Let's treat this with HNO3, and then they told us it's optically inactive. Okay, so we know that nitric acid will oxidize both the aldehyde up here and the alcohol at the bottom, but nothing else. So up here we get an acid, and down here we also get an acid. Okay, we know what's down here. This alcohol at the bottom, and they told us that this thing is optically inactive. Okay, so how do you think that we will use that fact?
For the product, would you put an OH group on the second carbon towards the right?
So up at this carbon up here?
Yeah,
Yeah.
make it miso.
Oh yeah, there we go. Yeah, so that's exactly the way to do it. Um, you can use the fact that this structure is going to be miso. And what we mean there is that we are able to draw a line going directly across, which is a plane of symmetry. Okay? So the only way for there to be a plane of symmetry is if this one up at the top is also an OH on the right. Okay? But we can't say anything about this carbon in the middle because, well, it could be either on the right or the left. Either way, it would still be symmetric. Okay? So from there, we can do rough degradation. And remember, this takes off the top CHO and then moves it down one. Okay? So bottom stays the same. This DOH at the bottom is still going to be the same again. We don't know what's right above it. And then we moved our CHO down one. Okay? And then let's look at the problem again. So then we reduced it with NaBH4. And from there, it's optically inactive. Okay? So let's reduce it. Okay? This is old news. We take the aldehyde, we turn it into an alcohol. Okay? And something up here. All right, and what do we do now?
You also put an OH group on the second carbon towards the right.
Thank you. Yeah, same thing. Okay? So we draw our plane of symmetry because it's optically inactive again. And there, whoops. And there we go. Okay? So, all right, cool. So we figured out what's left at those two carbons. So the final structure, or I guess the starting structure, is it has an aldehyde up at the top, so it's an aldose, and then CH2OH. It's a D sugar, and then there's two more carbons. So we know that this one right above was on the right, and same thing with the one up here, actually. There we go. Okay. So that's our final structure. I think the worksheet has a whole bunch of structures, and you can name this. Let's see. Oh, I guess it's ribose. That's kind of neat. Okay, cool. So this is. Where's my mouse? There we go. Great. It's ribose. That's exciting. Okay. So yeah, there we go. That is what we started with. Okay, let's see. Am I gonna have room? Yeah, okay, I've got plenty of room. Okay, let me get, whoa. Okay. Um, Let me get the next problem. Where is it? Oh, it's up here. Okay. So we have a disaccharide, and it is a non-reducing sugar. Okay. Uh, so I didn't mention anything about non-reducing sugars before, but what can you tell me about non-reducing sugars? What is like, uh, what is different about them that makes them non-reducing? Like you won't reduce them.
I think they're usually acetals.
Yeah. Yeah, exactly. Okay. So normally we have, okay, let me draw glucose here, right? And, it can be up or down, whatever, right? But actually, how about I draw it the other way? Okay, but here we have that if we just look at this carbon that has two oxygens there, so one of them is an ether and the other one is an alcohol. Okay, so this is a hemiacetal. Okay, which is reducing. Right? The naming is a little bit weird because reducing sugar means that it can get oxidized itself. Like it reduces other things, and in the process, gets oxidized. So the naming is a little bit weird, but yeah, if it's an acetal, we can choose anything else to be there, whatever, uh, as long as it's not like a hydrogen. Okay, but if it's an acetal, then so acetals are more stable than hemiacetals. Uh, so it's harder to come apart. So it doesn't oxidize as easily. Okay. So okay, all right. Let's go. Let's look back up at the problem and see what we're working with. Okay. So it's a non-reducing sugar, meaning that both of the anomeric carbons. So okay, uh, something is a reducing sugar specifically if it's an acetal at that anomeric carbon. Okay. So in this problem, uh, so both anomeric carbons are involved in some sort of bond, right? So like a CO and a C bond. Okay. Uh, we don't know what's on any of those anomeric carbons, but uh, we know that they're both tied up in bonds. Okay. So hydrolysis only gives D-glucose, meaning that all that we're going to be working with is D-glucose. Okay. Uh, so hydrolysis only gives D-glucose, and the other thing up here is that if we methylate it, so we put a methyl on every alcohol that's not tied up in bonds, and then we hydrolyze it, then we get this. Okay. And to skip going through all the nomenclature, to actually draw that out, what that structure is over here. One OMe down, an OMe up, an OMe down. Okay. So we have two of these things, and there's some spot that connects the two of them. Okay. So does anybody want to take a guess and tell me where the two of them are connected? Like which two carbons on each of them connects the two? Anybody? So we methylated first and then hydrolysis. Okay. So these methyls went on first to some alcohols that weren't tied up in bonds. Okay. So the important thing is we know that none of these positions could have been involved in bonding. No methylated positions involved in bonding. Okay. So great, there we go. It was for both of the two glucoses, they're bonded at the anomeric carbon. But huh?
How come anomeric carbon wasn't methylated?
Um well, we were told here that hydrolysis gives only this. So it's methylated at the 2, 3, 4, and 6 positions. Um, so we methylated first, and from there hydrolyzed it. So the only things that were tied up in bonds were over here. And then these things that did get methylated were free alcohols. They were just like open and available uh, at first. Yeah. And I guess to like go through and do the labeling. So like here's 1, 2, 3, 4, 5, and then 6 up here. So this is like, methylated at 2, methylated at 3, methylated at 4, and methylated at 6. So like it was up here. Yeah. So let me open up a new. Oh, okay. And oh, where am I? There we go. Okay. And let's see if I'm able to select what I drew over here. Now I copy this and paste it. Oh yeah, there we go. Okay. So I can slowly drag this up the page. Okay. So this is the only hydrolysis product, and we get 2 of them. Which indicates that whatever we started with must have looked like this glucose, and all of these are free alcohols. Like they have hydrogens, they're not involved in bonding. Okay? And then we had another one also. Same thing. Okay. So we know that the bonding was over here on this one and over here on this one. Okay. So for both of them, they're bonded at the anomeric carbon, which means that what we started with looked like, here's like a glucose, and then that's messy. Okay. So, I mean, so yeah, here's one glucose, and here's the other. Okay. Uh, cool. So is that it? Maybe I should ask, is this the only possible structure that we could have started from?
I think there are three possibilities.
Okay. What are the three possibilities?
I guess one where you have two betas, two alphas, and then one beta, one alpha.
Yeah, exactly. So what I drew here is this one's pointing down, so this is an alpha, and this one's pointing up, so it's beta. Okay. So I drew alpha plus beta, and then you also have alpha plus alpha and beta plus beta. Okay. Um, so I also drew this in a kind of weird way, right? I drew it like stacked on top of one another. So the reason I drew it like that and not like, let's say this, was because once we've done that, then we've had to flip this other one. So then we wouldn't have D glucose anymore. We would have L glucose. Or you can go through and redraw this other one in a way that it does have this the O up here, but it'll get a lot more complicated because then you have to like flip your molecule around a whole bunch, and these are already some fairly complicated structures. Um, so it'll be really easy to get lost. Okay, so that's why I drew it up here in this form. And well, let's see if I can kind of do something similar for these other ones. Okay, so it'll look a bit silly, I guess, but we're avoiding dealing with all of the stereocenter, you know, uh, difficulties and all of that. Okay, so we want this one to be alpha, and so we start up here. This one faces up, and then we alternate. There we go. And it's alpha, so this last one is down. Okay. And then from there, let's see. If we want to be a little bit lazy, then we could do something that looks like this and just say it goes back up around. Um, Personally, that is what I would do because that way you could just draw the same structure and just loop it up around. Okay. Uh, if you wanted to like really draw it out, uh, like in a kind of proper way, then what you would draw is, let's see, something that looks like that, and then OH down, and then it alternates. So yeah. Yeah. So if you went through and did all of it, and you wanted to draw it in this form so that it's like, uh, there's a clear advantage to drawing it this way, which is it's just a lot nicer. If you wanted to draw it this way, you'd have to move this O down to the bottom left. And from there, you could see how it would get complicated, right? Where does this thing go if you want to move it to be in that orientation? It's a little bit more complicated. It is facing up, and then from there you can alternate around. But yeah, I probably don't have to be the one to convince you that this is a little bit more complicated, which is why I prefer, uh, doing it this way, which is a little bit silly, but it works. It's a lot easier to keep track of. Okay. And then beta plus beta. So now we have, let's see, one of our glucoses, and we alternate. There's one of them. Okay, beta, so it's pointing up. And, well, let me do the whole looping down thing again. So now we have another beta pointing up again. Okay, and then the rest of our structure is exactly the same. Okay. So let me draw out the like, equivalent version of this. What I drew on the left. So if you want to go through, it could be like a good practice to uh, draw out, to actually like figure this out and see how it works. But it's probably a little bit more complicated than it's worth. So yeah, and this one will be up. While I draw this, does anybody have any questions about this problem, what we did? Okay. So it's silly, but like, here we drew alpha, alpha, and here we drew beta, beta. And then here's alpha, beta, which is the one that looks a little bit less silly, even though earlier it looked ridiculous. Now, compared to these, it's nothing. Okay. And then, if we look at the rest of the problem, there's a part B. And whoops. Go. Yeah, let me get part B. So part B is just if only alpha glycosidases will hydrolyze it, then what's its structure? Meaning let's see, where is this thing? Okay. So what this means is you can only break it down if there are alpha linkages. Yeah. Yeah, and I think on top of that, it's only if there are alpha-alpha linkages. Um, but I'm not certain. The important part is just like it's if there are alpha linkages. In most other problems, it would be like so here it's only different because it's bonded at the anomeric carbon for both of the sugars, and in most sugars it's only bonded at one of the anomeric carbons. So uh, it's not as uh, much of a consideration. But in this case, we'll say, okay, only if there are alpha-alpha linkages. So so it can only break down the one that has two alphas. Uh, okay, so that means it would be this one up here. Okay. So this is the structure that it is at the end. Okay. Good. Uh, any questions about this one? Nothing too wild in this problem. The following ones get a little bit more complicated. Paste it in, okay. Oh wow, I just rotated it. All right, let's see. Oh, that's way worse. Yeah, okay, all right. Okay, I undid. Okay. I've been figuring out this, broke Photoshop a little bit more recently. Like earlier, I copy and pasted my own drawing. I was pretty proud of that one. Uh, but apparently, I don't know how to use it very, not well enough to know how to rotate things, or at least unrotate things when I do on accident. Okay, here we go. So disaccharide. So we've got two sugars. Okay, and it's a reducing sugar. So can anyone tell me what that tells us, what we know about it being a reducing sugar?
It's a hemiacetal.
Yeah. And so we have a hemiacetal. Yeah. And in particular, it tells us that we have at least one, but you usually don't. I don't know if I've ever really seen an example of a disaccharide which isn't bonded at one of the anomeric carbons. So, what that tells us is that one of the anomeric carbons is a hemiacetal. Okay. So this time it's not going to be a, 1-1 linkage like in the last problem. It's not going to be a linkage between two anomeric carbons. Okay. And they tell us, okay, it only forms D-glucose when we do hydrolysis. So, all right, well, that means we, started with only D-glucose. Cool. Or the disaccharide is made of two D-glucoses. So so we know what we're working with. Uh, two glucoses, two D-glucoses. Uh, Nobody talks about L-glucose very much. All right, okay, I got plenty of space. So let's see. If we react it with silver oxide and excess iodomethane, okay? So what does silver oxide do? Does anybody remember? We didn't talk about this one explicitly this time, but you've seen it before.
It like makes, doesn't it make the methyl group more electrophilic on the CH3 and but for the iodomethane? Like it's a complex or no?
Oh, does it?
Did we use it in one of the eliminations?
Yeah,
Like
so that's what I was
Cope or
thinking.
Cope or the other?
Yeah, so it was used in the Hoffman elimination.
Yeah, the other, yeah, that one.
Oh, maybe it is used to when you methylate. Oh, hey, yeah, it is. Okay. Yeah, so all right, never mind. I was thinking of the wrong thing. So, well, it is used in the Hoffman elimination for sure. But whenever you use it, uh, whenever you methylate to completion, like in this case, you use silver oxide. Um, let's see. Oh yeah, okay. So, well, I'm looking in the book right now. So yeah, the book says that silver oxide does polarize the iodomethane bond, which, well, that's interesting. Yeah, cool. Okay. Uh, so yeah, okay, all right. So this is just the reaction conditions then. So we're just methylating to completion. Okay. So octamethyl derivative, which means that there are 8 free alcohols. Okay. And then if you hydrolyze it, so we get an equivalent of 2, 3, 4 triomethyl glucose. Okay. So that means we get uh, here was an OH. They didn't say anything about the 6 carbon, right? So 2 so this is the 4 carbon, the 3 carbon, and the 2 carbon were the ones that we get out. Okay. And there we go. All right, yeah. Uh, so we get one equivalent of this thing, and see, where am I lost? Okay. Yeah, and this 6th carbon is free. Okay. So over here we get, an OH that's hanging around. And we're not worried about this OH because this will be the one that presumably we can reduce. Okay. The fact that this OH up here is not methylated is kind of the interesting part. Okay. So let's see, and it's an octamethyl derivative, and so the other one that we get is, let's see, so we know the other one is bonded at the anomeric carbon. Okay, so this other one has an OH hanging off like that, and it's methylated all over. Okay. Uh, so okay, there are 1, 2, 3, 4, 5, 6, 7 methyls in this case. Um, so okay, we know that this one can't be methylated more because there's only one place for it to bond, and this one should probably be methylated at this anomeric carbon. I am not super certain on why they said that it's not methylated. All right, we'll take it as methylated. Unless does well no, I think yeah, using iodomethane and silver oxide methylates the anomeric carbon too. So this should be fine. Yeah, okay. It should be I think it should look more like this. So in that case we have this anomeric carbon and this 6 carbon up here to work with. Okay. And we also have that the disaccharide can be hydrolyzed by a beta glucosidase. So uh, so we know that this one is beta carbon because of the beta glucosidase. Yeah, there we go. The beta glucosidase hydrolyzes it. So this one has to be a beta carbon. Okay, and so from there, let's see. Let me use my newfound skills to. Oh no. There we go. Copy. So I'll save this and make a new file. Yes, I want to save. Okay. I'll copy and move this up, which means okay. Yeah, so we have this sugar up here with this free alcohol. And this one's also free. So what that means is that we go backwards, and what we started with was an anomeric carbon here because it's a reducing sugar. And we know that at the end we only get glucoses, right? So, okay, that means we go up here and then we alternate. Okay, and so we have this oxygen up here. And this is where our bond is, and the bond is to the anomeric carbon of the other one. And it's also beta. So that means it's facing up. Okay, and we draw out the rest of our structure. Alternate like that, and there we go. Okay. So that would be it. This, a lot of times you might see this written as like, so this linkage will be labeled as a beta 1,6 glycosidic bond, I guess. which kind of tells you all of the information that you need, right? This is a beta carbon, and it goes from carbon 1 over here. Yeah, I use red to label, right? So carbon 1 to carbon 6. And this one over here is beta. There we go. So let me put this in green. Oh, that is too big. There we go. Okay. Any questions? Did I make any mistakes? Okay. Oh no, I didn't press that. Okay. Right, one more of these. Okay, let me not use green anymore. Oops. Oh, okay, that changed things. Oh. All right, whatever. Okay. Go on to here. Make sure. Okay, there were no chats or anything. I didn't miss any questions. Okay, so one more. Let's see. We have a disaccharide. It's a reducing sugar. And I'll spare you the question from me again. The fact that there's a reducing sugar means that there's one anomeric carbon. Okay. Really, it means there's at least one anomeric carbon, but glycosidic bonds will really generally be with one of the anomeric carbons. So one of them will be tied up in that glycosidic bond. The other one will be free in this case. Okay. Let's see. Acidic hydrolysis gives one molecule of D-fructose and D-galactose. All right, so we're not working with glucose anymore. So how about I draw the structures of what those actually are? So if we do hydrolysis, then galactose is pretty similar to glucose. Yeah, see this, just this one carbon is flipped compared to what glucose is. Does anybody remember what like the name is for galactose in relation to glucose?
Was it like the C carbon for epimer? Epimer?
Yeah. Yeah, so these two are called epimers. If you just flip one of the carbons. Yeah. Oh, I can't remember if this name is for more than just sugars or only sugars, but well, okay. Yeah, glucose and galactose here. I should label it. Glucose and galactose are epimers. Okay, both are 6 carbons, both are aldoses. They're just different based on their stereochemistry at a single carbon. All right, anyway, so we also got D-fructose, which is definitely not an epimer of glucose. So this is our this is the first pentose we're dealing with for the day. OH down here, and then yeah, there we go. Okay. So this is the two things that we've got. All right, let's see. Invertase enzymes hydrolyze glycosidic bonds forming at the anomeric carbons of the anomeric centers of fructose and is not affected by them. Okay? So from the whole invertase thing, we know that the glycosidic bond is not at the anomeric carbon of fructose. Okay. Meaning it's at the anomeric carbon of galactose. Okay. So the anomeric carbon of galactose is bonded to an oxygen, which is bonded to fructose at some position. Here we go. Alpha galactosidase cleaves the molecule. Okay. So which means that we're working with alpha galactose. Okay. Great. Now all we need left is to tell where that anomeric carbon of galactose is bonded to on the fructose. That's all we need. All right. Disaccharide treated with silver oxide and iodomethane. And then we hydrolyze it and we get, let's see, these two things. All right, how about I draw these out? So methylation and then hydrolysis will get you, let's see. So from what the problem says, it'll get you an OMe there. Okay, this alpha anomeric carbon, or sorry, this alpha anomeric alcohol, we expect to be okay because we methylate and then hydrolyze, and we know that it's involved in the bond. So from there, O-methyl here, O-methyl, and the O-methyl is pointing up. Because remember, this is not glucose, it's galactose. All right, and then what they tell us in this other one is that we have, here's our pentagon. Okay. And they tell us that, we have two alcohols. Let's see, let me go back. Oh, did I miss one? Oh, yeah, I did. Okay. All right, here we go. So going all the way up here, so it's 1,3,4 tri-O-methyl fructose. So let's see what we got. We got the 1 position. We got, this is 2. We got 3, and we got 4. Okay. They didn't say anything about 2, and they didn't say anything about this 6. Okay. The 2 and 6 were left unmethylated. Okay, so we know that we have either a bond here or we go over to here. All right. And based on which of the two of those it is, then that'll solve the rest of this problem. So, does anybody have any ideas about which one of the two it is? Maybe let me go up a little bit. So here, yeah. Here's the problem, and I'll slowly go through what we've worked out. Okay, so we know that hydrolysis is like this. We saw about invertase. We know it's at the anomeric carbon of galactose. Cool. We know it's alpha galactose. And we know we get this from methylating.
Is it at carbon 6?
Okay, what makes you say carbon 6?
because um, in the beginning it said it was reducing, so we have to have acetal over.
Ah, okay. Uh, oh yeah, I guess that, yeah, so I guess that works, huh? Yeah. Yeah, if you have this ketone, because this is, here this will be a ketose, not an aldose, right? So here will be a ketone. Um, and, oh, I drew one carbon too many. Uh, yeah, and so if it's a reducing sugar, then you know that one of the anomeric carbons has to be open. This one's clearly not because it's involved in a bond, so this other anomeric carbon has to be open. Okay, yeah. All right, so it'll be a number 6.
What was your reasoning? Do you have a different?
Yeah, I do. Uh, does anybody know what my reasoning was? See? So, okay, my reasoning was that from the invertase, we knew that the glycosidic bond wasn't at the anomeric carbon of fructose. So this is the anomeric carbon of fructose. So then we knew from invertase it had to be at 6. But I like the reducing sugar thing too. I guess both of those, yeah, I guess both of those tell you the same thing. Uh, I don't think either one tells you more information than the other two. So, well, I guess, yeah, I guess invertase tells you that it's you use the galactose anomeric carbon, not the fructose one. So I guess invertase actually tells you more, maybe. Whatever. Either way, all right. Let's draw the structure out. So, whoops, not methylated, right? This OH is up. This one's also up, down. We know that this one's alpha, and alpha is down, right? So put alpha there. Okay, and now it's at that 6th position. So for fructose, where were the rest of them? This one's up, and this one is down. There we go. Okay, and that matches all of what we were looking for, I think. So this is uh, galactose here, and this one was fructose.
Could you go over the reasoning behind the invertase again?
Yeah. Let's see. So let's go up here. Okay. So invertase enzymes hydrolyze glycosidic bonds which form at the anomeric centers of fructose, and this molecule is not affected by them. So what that tells us is that, well, the glycosidic bond then is not at the anomeric carbon of fructose. So that means it's going to be at the anomeric carbon of the glucose. And we especially know that it's going to be at the anomeric carbon of the oh, did I say glucose? It's going to be at the anomeric carbon of the galactose. And we especially know that because it's cleaved by an alpha galactosidase, which specifically cleaves disaccharides that have an alpha bond at the anomeric carbon of galactosidase. Okay, so this invertase tells us that this won't happen because if it did, then we would have a sugar-sugar bond at this anomeric carbon, and then it would be affected by invertase. So it has to be at this other one. The alternative is also that this they told us it's a reducing sugar, and we know that one of the anomeric carbons has to be open. So we know from the alpha galactosidase that the one on the galactose is not open, so the other one has to be open. That's the other way to look at it. Are there any other questions that anybody has? Anybody? Okay, so that is all that we have for today. Let me save this. Okay. So I will also there's like like last week I also had like this sign-in spreadsheet. Here I sent a link in the chat. If it would be great if people just signed in. It helps me count, how many people came. I promise it doesn't actually record who you are. It just records how many people. Like, throw your number in. Can you guys edit? No, you can't. There we go. Okay, I think you should be able to edit now. Yeah, just whenever you get the chance, just throw your number in there. It's, whenever you get the chance. Okay. Are there any questions about any other questions? How about I stop recording?